the class which supports the Juniper-Mist certifications, the JNCIA and JNCIX Mist certifications you can do. I also was involved in writing the exams. And it's a 4-day class. If you're working with Mist, I would really recommend it. What I've been asked to do today is do the sort of best bits. So a 4-day Mist class in an hour. Okay, that's what we're going to try and achieve. I don't actually know how long we've got. We've maybe got a little bit longer, so we'll see what we get in to. So I want to tell you a little bit about the class first, and then we'll look at some different elements from it. And this is the course contents. And I spent actually a long time, probably longer than you'd think, working out what the outline and what should actually go into a class. And it's maybe a little bit different to standard vendor training that you may have done. I think a lot of vendor training is often click here, press this button, do this, here's some steps, and then you can achieve this. I didn't want the class to be like that. So after our course introduction, where we introduce ourselves, we go into chapter 2. And chapter 2 takes the whole of day 1. Okay? And it's an introduction to Wi-Fi basics. We don't really mention Mist at all on day 1 of the class. We just talk about Wi-Fi as a technology. And the reason for that is when you click a button in Mist, I don't want you just to know you need to click this button. I want you to know what it's doing and why it's doing it. So the first part of the course is all about Wi-Fi basics. Wi-Fi as a technology, how does it work? And we spend an entire day on that. And I'm going to show you a little bit of the content from day 1 to show you just what level of detail we go into on Wi-Fi. But it's all about it's a little bit like a cut down CWNA course in a day, but it's looking at all the elements which you need to understand if you're going to configure a Mist wireless network. So that's day 1. Day 2 is where we look at chapters 3 and 4 up here. And it's about, okay, now you understand Wi-Fi, let's configure a wireless network. How does a Mist network work? How do you claim access points? How do you get an SSID operating? How do you get clients connected? How do we get we're really on the deploy stage in configuration of a new system, and we look at how to build a Mist network. We understand the architecture, we understand when we use a Mist edge, and we go through that entire process of getting the system up and running. So that's day 2. Day 3 is when we go into network operations. Now you've got a network and a Mist network up and running, how do you manage it on an ongoing basis? How do we monitor it? How do we look after it? So that's what day 3 is all about. And we cover network operations, we covered wired assurance, we cover Mist, we cover the sort of Marvitz features in that day. And then the final day, day 4, is split into 2 sections. In the morning, we look at location-based services. So we look at how Mist does location. It's a really fun morning, actually, because Mist does location in quite a unique way. And we actually start off looking at location generally and then how Mist does it differently. And we do a few demos as well. I have some APs set up and we look at some of the demos in it. And then after lunch, it's all about automation and scripting, which is another really key feature of Mist, is that it's what I would call it's API driven, and it's API first. So when Mist implement a feature, they build the API for it first. If you're in the Mist UI, in the web UI, and anytime you click a button, and I'm going to show you this in a little bit, but every time you click a button, you're generating an API call. That's what you're doing. So the way you control Mist and the way you get data from Mist, the way is all doing API calls. When you're using the UI, you don't know it, but all you're doing is interacting with the API through a GUI. Why is that so important? And why do I think it's incredibly unique, really, with Mist, is you look at your vendors out there, and you want to do any sort of integration with them. They tend to build a system first, a UI, a command line, and then they think, what should we make available to the API? And they start writing some API calls. But you can only get access to the data, to the functions that they make available via the API. New features, you've often got to wait 6, 8, 9 months before they make it available to the API. It's not the case with Mist. It's made available in the API first, and then you get the features in the UI. So there's nothing that you can do in the UI that you can do with an API call. There's no data available in Mist that you can get via an API call. That means you can literally build any custom applications you want in Mist. In fact, I know some Mist customers that never use a UI, they've just got their own custom applications written, and that's how they interface with Mist. Where they've got an application for deploying a new site, and it automates it all for them. They've got an application for doing this, for doing that, and they just literally interface with Mist purely using the APIs. So we only have an afternoon on it in the course for the Let's Day, but we get into we go through what's available in Mist, and what APIs are available, how they work, and we look at some like pre-written scripts so that you've at least got a starting point if you want to get into doing some API stuff. So that's a 4-day class. Love to see some of you on the class, especially if it's one I'm teaching. There's a few instructors that teach the classes, but it's a great class. What we're going to spend the next bit of time doing is just looking at some of the elements of that course. And I thought I would love to show you some of the detail we go into on just the Wi-Fi, the general Wi-Fi stuff. I probably won't, I've got a few selections of the slides in here, and I probably won't go through it all in detail, but I thought it'd be good for you to see what sort of stuff we cover and why. So first of all, a few slides from the wireless LAN concepts. And here's one which is a really important concept which a lot of people don't realise with Wi-Fi. And that is that when a Wi-Fi signal leaves an antenna, or leaves an AP, if you want to think of it, is how fast that power drops off. So as the signal travels away, how fast the power drops off. And it drops off, and we call the way it drops off something called the inverse square law. And let me explain what the inverse square law is to you. If I was to take a particular distance from an antenna, and we're going to call that distance R, and I measure the power at R. So whatever the power is, I measure it. If I go twice that distance, that's 2R. The power is a quarter of whatever the power was at R. So I double the distance, my power's a quarter. Or if we're looking at that in dB, that would be 6 dB difference, if I then go to 4R, it's 1/16 of the power it was at R. Why is that so important to understand? Well, let's just pretend, this is an antenna here. Just for you to realise how fast the power drops off. If I measure the signal at 1 centimetre from this antenna, whatever the power is, I've measured it at 1 centimetre. I go to 2 centimetres, it's now a quarter of that power. If I go to 4 centimetres away, it's only a 16th of the power it was at 1 centimetre. And it would be exactly the same if I did that in millimetres. If I go 1 millimetre away and I go to 2 millimetres, the power's a quarter of what it was. So what does that mean in reality? Well, we called it the way the power drops off something called free space path loss. That's just the amount of signal that's lost as a signal travels over the air. And if we plot that onto a graph, you will see that as you first leave the AP, the signal's just dropping off almost in a straight line pointing down. Hardly travelling any distance from the AP, and I'm losing all my power. In fact, over the first metre, we lose the majority of the power that we transmit from an AP, just over the first metre. If we take a look at this example here, we've got the 5 gig radio transmitting at 14 dBm. By the time I get to 1 meter, it's at minus 33 dBm. That's like what is that? That's a 47 dB drop. And if you think 10 dB is 10 times less power, minus 10 dB, and we've got minus 47 dB, so 100,000th of the power, you can see just how much we've lost over that first meter. So we lose most of the signal we transmit over the first meter when we're transmitting wireless. After that, you can see that obviously between 1 and 2 meters, it gets a quarter of the power, that's minus 6 dB, so we lose 6 dB, it goes from minus 33 dBm to minus 39. Between 1, 2 and 4 meters, another 6 dB is lost. So this curve gets less and less and less as we move away from the AP. So it's important to understand this, because when we're thinking about RF, we want to appreciate how the power is lost and also what effect that has on users, depending on what distance they are from the AP. Another thing that you'll notice as we look at this graph here is that if we look at the power here, that I've got 2.4 gig 8 dBm, 5 gig 14 dBm. When we get to 1 meter, 2.4 is 32 dBm and 5 is 33. They're nearly the same within 1 dB of each other, but they started off 6 dB different. Why is that? Well, let me find something I can show as a little example here. Piece of paper. I want you to imagine this bit of paper is a 2.4 gigahertz antenna. Okay, that's what I want you to imagine it is. Now, antennas have something called a receive aperture, how much of the signal they're going to receive. And it's proportionate to its wavelength. And if you know the wavelength of a 2.4 gig signal, it's around 12 centimeters. And a 5 gigahertz signal is around 6 centimeters, so about half. And therefore the receive aperture is also about half. So this is, if you imagine, this is how much signal a 2.4 gig antenna receives. Let me show you what a 5 gig is. I'm just going to fold a piece of paper in half. And I'm going to have to do it in half both vertically and horizontally. Okay, this is now how much signal a 5 gig antenna receives, because I've halved it both horizontally and vertically. So if we're looking, comparing it to my 2.4, it's receiving 4 times the amount of signal. 4 times, well, every 3 dB is double or half. So it means that it's receiving, if it's a 2.4, it's receiving 4 times the 5 gig, it's about 6 dB more or less. And that's why when we talk about RF signals, people often say 5 gig doesn't go as far. It's not nothing, or it attenuates more, or it goes just as far as 2.4 gig signals. If you had an AP and you set 2.4 at 100 milliwatts 5 gig, those signals would hit the moon at the same time. They would both travel. It's just when we receive it, the receive aperture of the antenna, we receive more signal with 2.4. So that's why, and it's about 6 dB more, it's why that if we offset the power at the AP, at the receiver, we can make them about the same. But if we have 2.4 and 5 gig at the same power levels, we'll always receive 2.4 stronger. Now, is that a problem receiving 2.4 stronger? Well, some clients, which AP do they connect to? They'll always connect to the strongest. So if 2.4 is stronger, they're always going to connect on 2.4. 2.4, we've only got 3 channels, not as much capacity, more interference, worse performance. So if we want to encourage our devices onto 5 gig, what we can do is when we're configuring our power is we can set 5 gig radios to be stronger than 2.4. And if we do a 6 dB delta, we're going to get more similar coverage at the receiver, at the client device. So that's free space path loss. Another really important RF concept, which a lot of people don't know a lot about, but is really, really important when we come to looking at client performance, is to do with something called modulation. Now, modulation sounds like a complicated word, but all it is really is how do we encode data into an RF signal? RF signals are often drawn in as a sine wave, but how do we make that sine wave encode data? If we've got a set of data, a binary string that we want to transmit over a network, how do I encode that into my RF signal? Now, on Ethernet networks and data and sort of cable networks, we often just use changes in voltage over a piece of copper, and we call it a baseband signal. That's what Ethernet uses. It uses something called Manchester encoding using a baseband signal. But over RF, we need to somehow manipulate the RF signal. Now, I'm not going to go into too much detail on this, but there's different properties of an RF wave we can manipulate. And early on in this course, before we get to this point, I've talked about all those properties. So we'll talk about what phase is, what amplitude is. We'll talk about what frequency is. But they're different things I can manipulate. So I could manipulate the phase of the signal. So if you just look at its very first sine wave next to the 0, you can see it goes up, down, and it's going back up. You'd normally expect that to carry on up. But we shift the phase. We're doing it by 180 degrees. Again, don't worry too much about the detail. So now it's going down. And that phase shift means we're going from a 0 to a 1. So that's one thing we could shift. We could shift the amplitude. So an amplitude is how high the peaks are of the RF wave. It's what the power level base is. So a low powered signal is a 0 and a high powered is a 1. That's something else we can do. Or we could transmit on different frequencies. I'm not going to go too much into that because in wireless networks we tend to use phase shift key or a combination of phase and amplitude. Now, why do you need to know this? Well, I want you to just understand, and again, I don't want you to get too much bogged down in the technical detail, but I want you to understand there's different modulation methods used in Wi-Fi. The most simplest form that we use is something called BPSK, binary phase shift keying. Sounds complicated, but it's not really complicated. All it is that we can either transmit a 1 or a 0 with binary phase shift keying, 1 bit at a time. Every transmission, or what we call in OFDMA, we call it a symbol. But again, we don't need to worry, but a transmission of a sine wave. Think of it like that. Every one we do, we're going to either encode a 1 or a 0. If we're going to transmit a 1, we send a sine wave. That's what a sine wave looks like. Plotted on my graph, you can see it peaks at 90 degrees. Okay. Now, if I can plot these sine waves on what's called a polar coordination chart, which is, I didn't bring my slinky spring with me today, which I normally use as a good example, but you've all seen slinky springs that climb down the stairs, yeah? If I stretch out a slinky spring in front of you, do you know what you'd see if you were looking at it? If I stretched it out and you were looking at it, you'd see a sine wave. But if you looked at it on the side, you'd see a circle. Because it's really just a circle or a coil stretched out. Well, RF waves are a bit like that. The sine wave is like looking at a circle over time, moving over time. If you looked at it end on, you just see a circle. And that's what this polar coordination chart is. So if we're looking at where it peaks, which is 90 degrees and up here is 0, I can plot my 90 degrees around a circle. And I'm going to say that equals a 1. To send a 0, I send a negative sine wave. A negative sine wave is the opposite of a sine wave. So this time it starts with a falling edge, goes up, it peaks at 270. So if I've got a signal that peaks at 270, which is over here, I'm going to say it's a 0. Now, why did I want to tell you all of that detail? Because I want you to understand another concept called an EVM. Okay? EVM stands for error vector magnitude. And this is how much error can we cope in our signal. What would happen if I send it, if you send, you know, a 1, but it gets a bit corrupted in the air. And what I receive is a signal that doesn't, you never receive a perfect sine wave. It maybe peaks here at 100 degrees. Or it peaks at 90, you know, 98 or 78 degrees. What happens if it's not quite perfect? Well, that's how much error we can cope with. And with this one, binary phase shift keying, we can cope with lots of error. If this dot hits here, if it hits anywhere else in this box, so +1 degrees or, you know, right down here, it's going to still be decoded as a 1. In fact, anything in this box is going to be decoded as a 1. So I can cope with quite a lot of error. Anything the other side is going to be a 0. So there's lots of room for error. The signal can be fairly corrupted and I can still decode it. But I can only send 1 bit at a time. And this is how we get our lowest data rates on Wi-Fi, 1 megabits per second, 6 megabits per second. That's how we transfer it using binary phase shift keying. But what if we want to go faster? That's a really slow data rate, isn't it? 6 megabits per second. We can do hundreds of megs per second, gigabit speeds on wireless now. How do we get there? When we need a better modulation method. So the next is something called QPSK. And I'm not going to go through all of these, but I just want you to get the concept in your head. QPSK, instead of sending 1 bit every transmission, it's going to send 2. Now I've doubled my data rate. I've gone from 6 to 12 meg. Okay, great if I can send 2 bits, but now I need 4 different values to get all my data bits, not 2. So, and that's where the Q comes from. It stands for quadrature 4. Okay, and it's a little bit more complicated, but again, I won't get, when we roll the detail, but we have the bits down this side, on the right-hand side, are going to be, a 0 is going to be a negative sign, and a 1 is going to be a sine. And then in the left-hand column, we're going to use a cos and a negative cos. So we've got our sine and negative sign on the chart. If I show you a cos, it peaks at 0, and the negative cos peaks at 180. So if you wanted to represent 1, 1, that would be cos sine, 1 peaking at 0 and 90. If you add those together, you actually get a peak at 45 degrees. Okay? When will we do? So 45 degrees on my circle equals 1, 1. And we'll just plot the other ones on the chart. I don't want to go over them in too much detail. Because we've not got 4 days for this course, we've only got an hour. But you can see where they are. But what does the thing I want you to see is what happens to my EVM box, my error vector magnitude. I've got less room for error. If I'm trying to do 1, 1 and I pick it up here, it's going to be decoded 0, 1. My box has got smaller. So I can do a faster speed, but I can only do it if I've got a good enough signal and I can go twice as quick. And these go on. We're not going to go through them all, but there's then something called 16 cram, which look, I've now got even more tinier boxes because now I'm doing quadrature amplitude modulation. So I'm also doing different power levels. So I've got 45 degrees at a low power and a high power. But now my EVM box is even smaller. So I can only do this, although I can now do 4 bits at a time, I can only do it if I get a better quality signal. When I've got a good quality signal, if it gets too low, I can't do it. And if we want to go faster, we go to 64 cram. 64 cram does 6 bits every transmission. But look at my EVM box, it's got even smaller. And believe it or not, 802.11ac introduced 256 cram, where we can now send 8 bits every transmission. But look how small my EVM box has got. Tiny. I can't cope with much error in my signal. It's got to hit that box. And you can see the different EVM boxes for the different signals. Why do I tell you all of this? Because I want you to realise that there's a correlation between the modulation method we use and the data rate. And ultimately, the data rate is going to affect wireless LAN performance. What speed can I transmit data at? And the way clients work is they'll always try and use the highest data rate. So if I'm a one spatial stream device on a 40 meg channel, I might be using 200 megabits per second. This is using 256 QAM and various things. What happens as I move away from the AP or my signal gets corrupted? What if I'm not very close to the AP, I'm not getting a good signal? Well, I'll then try and use a lower data rate and a lower one and a lower one, and I'll start moving towards it 6.5, where I'm using binary phase shift keying, the first one I told you about. So as you move further and further away from the AP, your data rates will drop off and get less and less and less. And these are showing you the Wi-Fi 6 data rates, which you'll notice they've introduced something called 1024 QAM. They can go even faster, but an even smaller EVM. You're only going to achieve that when you're really close to the AP. So I tell you all of this because I want you to understand the concept of dynamic rate shifting. As I move further and further away from the access point, my data rates are going to drop off. As my, what we call signal to noise ratio, how much signal above the noise floor, as this gets less, my data rates are going to go down. So access point placement becomes important. If I'm taking an access point and I'm going, well, we don't really want that on this display, so we'll put it inside the ceiling. Now the signal has to penetrate the ceiling before it gets to me, which means what? I'm going to get a lower quality signal. I'm going to have to use a lower modulation method. I'm going to get a lower data rate. If I put the AP out in the corridor, because out in the corridor it's just easier to maintain and it covers 2 rooms as opposed to just 1. But am I working in the corridor? No, I'm working in the office. So now that signal's got to penetrate a wall, and before I've started, I'm running out in a lower modulation method, lower data rate, worse performance. So my number one rule for wireless design, always, put the access points as close to the users as you can. Where are your users working? That's where your access points need to be. If you put an access point in an office where everyone's got a wire plugged into a docking station, and actually the conference room over there, through the corridor on the other side of the wall, is where everyone works wirelessly, but the AP's over here and not where the wireless users are. Put an AP where the wireless users are. Because by the time the signal's got there, they're going to be on a lower data rate. And then you've got 20 people in the conference room, all on a lower data rate, all sharing the lower data rate between them, and the per user throughput is going to be way down. So if we want to create good, high-performance networks, access points as close to the users as possible. Always works better. How can we monitor it so? How do we know if a user's got a good Wi-Fi signal or not? That's a key thing. It's okay knowing the theory, but what do we do about it? Well, there's 2 ways we can look at it. We can look at it from an AP point of view, and we can look at it from a client point of view. And Mist does give us great statistics on client statistics, where I can see the signal strength, signal to noise, and I can see the transmit and receive physical rate. I can see what data rate they're using. So I can determine that actually, if my client's getting, the network's performing really badly, but they've got a good RSSI, they've got good signal to noise, and they're operating at a really high modulation method, top data rate, the RF environment's good. And that's not what's causing the problem. It might be a network issue behind the AP. But that's one thing I want to determine. Is it the network or is it the RF? Well, by understanding this and by being able to monitor it, I can start to answer those questions. Who's at fault? Where's the problem? We can also monitor using client applications as well. So you can also look at this stuff on a client. If you've got a Mac, there's a tool called Wi-Fi Signal I would really recommend. If you've got a PC, then I've written a little PowerShell script, which is here. If you go to my website, mackenziewifi.com, there's a link to download it. It's just a PowerShell script. I wrote it in response to sit in a class where someone told me that PCs were rubbish. There's a whole PC-Mac debate. I'm not going to get into the argument today. I'm on the PC side. I know a lot of people will be on the Mac side here, but they were one reason they told me that it was rubbish was because we didn't have Wi-Fi signal and they did for Mac. So I basically said, well, you've got NetSH and you can do show it wireless LAN interface and you get the same information. And I got, well, yeah, but then you've got to keep pressing it again. So I was like, well, you could write a script to just replay it. And then by the end of the class, I'd written its little tool. So that's where that came from. But it's free to download for anybody who wants to use it. And again, we can see transmit data rate and signal strength and various other information that we'd want in there. So now you understand a little bit about RF, and I hope that's interesting. Another thing that we talk about a lot on day one of this class is how do clients connect to a network? What process does a client go through? Now in the 802.11 sender, there's this lovely state machine which goes through it all. And on the class we go through each step in quite a lot of detail, which I'm not going to do now because we don't have time. But what we do is we go on to talk about the connection process. And the reason it's important to understand it is because one of the issues that often affects wireless clients is they not being able to connect to a network. And Mist monitors that process and it will tell you where it goes wrong. But if you don't understand that process, then you may not understand what Mist is telling you. So we go through the entire client association process. I'll quickly go through this slide and just tell you the sort of process that clients generally go through. Once the client's discovered a network, so first of all it has to discover a network, and we chatted about this a little bit this morning, passive scanning and active scanning, that's what's changing with Wi-Fi 6E. When it discovers, if you think about a client, I'm going to sit here and go, which AP, I need to find APs. Is there any APs out there? And I'm going to discover potentially more than one access point. And then the client has to decide, well, who do I connect to? What do you think I pick? Let's say I've discovered 5 access points. Okay? Which one do I connect to? Anyone? Flip a coin? How do I do it? Now, the truth is, clients make the decision themselves. There's no standard for it. So some clients may pick the strongest. Some may pick the lowest SNR. Some may prefer 5 gig over 2.4, so they look at the frequency band. They may look at channel utilization. They may look at neighbor reports from the AP. They may look at how many clients are connected to the AP. There's lots and lots of things they may do, and all clients do it differently. So it's really, really hard to predict, but all clients do it. And once they've picked an AP, they're going to follow a process. And the first thing they're going to do is go through something called authentication, or what I call 802.11 authentication. And it's important to understand what 802.11 authentication is. I am not talking about pre-shared key authentication, 802.1x authentication, all of that happens later. In the original 802.11 standard, they provided 2 authentication methods, something called open system and something called shared key. Open system was allow anyone on, no authentication, everyone can connect. The other method, shared key, was part of the WEP security suite, wired equivalent privacy, which the original standard came out in 1997, and the first white paper describing how to crack WEP was published in 1999. And since that date, tools have been come out where you can crack a WEP key in under about 10 minutes. We don't use WEP anymore. So we don't use shared key. So if we don't use shared key, we don't use the shared key authentication method. So that leaves what? open system authentication. No authentication, but you still have to go through it. It's a state machine. So most clients will still go through open system authentication and you'll get an open system response. Now that is changing with WPA version 3. There's something called simultaneous authentication of equals, which you could do at this stage. But we're not going to get too much into that detail. And if you're roaming, you might go through fast authentication. But most clients today still will always do open system authentication. First thing they do. Can I connect? Yes, you can. It'll never fail. Should never fail. It's no authentication. But it's all 2 packets that are transmitted. Once we're authenticated, we then have to associate to the AP. So we send an association request. We get an association response. If that is successful, we'll get a little ID called an association ID, uniquely assigned to us on that network. Once we have associated, being associated to an AP is like having a connection to a switch. You know, you plug in a bit of Ethernet cable, you get a little blinky connection light saying you're connected. That's a logical equivalent to being associated to an AP. I'm connected to the AP. But just like when I plug into a switch, does it mean I can get to the network? Maybe. But if there's .1x on the port, I've got to authenticate, don't I? The switch won't let me to connect. It's the same with an AP. Can I connect when I'm associated? Well, it depends. If it's an open system, yeah, I'm on the network. But if it's got WPA, then no, I can't. I've got to go for some further authentication, either using a pre-shared key or using 802.1x. So that comes next. If I'm using 802.1x, I do the 802.1x authentication with a radiate server, and then I do a 4-way handshake, which is where we exchange all the encryption keys. If I'm using pre-shared key, I go straight to the 4-way handshake. Great, I've got wirelessly connected to my AP and I've passed authentication. But am I connected to the network? Well, there's still many things that could go wrong where a client would go, the Wi-Fi doesn't work, I can't connect. Because the next thing you're going to do is get an IP address. How do you get an IP address? Well, we go through DHCP. And then we go through a process called DORA. Again, I'm not going to go through it all today in terms of time, but we go through that. Following that, once I've got an IP address, I'm going to do something called, and I'm going through this quick, than I do on a course, but we're going to do something called gratuitous ARP, where I basically just check, has anyone else got my IP address? Is there a duplicate IP address? Then I'm going to ARP for the default gateway, find out the IP address of my default, the MAC address of the default gateway I've been given with DHCP. And then I'm probably, if I've got internet connectivity, going to do some sort of DNS query. Now, all of these things are needed for me to get connected to a network and have internet connectivity. If any of these things don't work, what's your users going to say? The Wi-Fi doesn't work. They're not going to say, I didn't get an IP address. They're not going to say, oh, DNS is down. They're just going to go, the Wi-Fi doesn't work, I can't connect. So we need to understand when that's the problem, where does it fail? And within Mist, they monitor each of those steps. And they're going to show you different, what we call classifiers for each of those steps, so you can actually see exactly where it fails within Mist. And that's one of the reasons we teach that process in the Mist class, so that when we get into the Mist dashboard, we actually understand what we're seeing and what's happening. I'm not going to go over Roman right now, but we teach a number of concepts which are useful to know. We teach a concept about how does Wi-Fi communicate. We talk about it being a shared half-duplex medium. That means only one person transmits at any one time. But who decides who transmits next? If we're all connected to the same AP, when is it my turn? Well, we talk through on this class the process that clients go through. And I've broken it down into 3 very simple rules. But basically, wireless, we listen before we talk. So if we hear somebody else talking, we don't talk. Having listened for a while and realised when the medium becomes free, we then do something else. We then wait. We're quiet for a bit of time. Between every wireless frame on a wireless medium, there's got to be a period of quiet known as an interframe space. And then what do we do following that? Do we transmit? No. And the reason not is, let's just say Let's say I've got a frame to transmit. Let's say Sleva also has a frame to transmit, so we both are waiting, but let's say, so I can't remember your name, you're transmitting a frame at the moment. Yeah. You're transmitting a frame. Okay, so you're talking. We both hear, we go, oh, we'll wait. You finish, and we both wait in interframe space, then what happens? If we both transmit, collision. It's not good, that. On wireless, we try and avoid collisions. We implement something called carrier sense multiple access collision avoidance. So what we do is after we've waited its minimum amount of time, we then both wait even further. So we're quiet for even longer. That's what we do. But it's a random amount of time. So Sleva's going to pick a random number, I'll pick a random number, and we count it down. Whoever has the shortest gets to go next. It's like a game, a bit like rolling dice. And that's how wireless contention works. So we go through all of that in a little bit more detail than I have. But what if after all of that process, we both pick the same number, random number, and we collide? Well, it's okay because wireless is reliable. Every packet we transmit on a wireless network needs an acknowledgement. So if there's a collision and I don't receive an acknowledgement, I go through that whole process again and try and retransmit my frame. That is wireless for you. So that hopefully gives you a bit of a flavour of day one of the class. There's some of the concepts we talk about and go through. Let's move to day two. One of the things I want to introduce people to on day two is Mist configuration. Because I want people to understand the way Mist is organised. And when you look at the Mist configuration, you can think of it as a set of configuration objects, things that we can configure, groups of configuration. And some of those objects are at what we'd call the organisation level. They apply to an entire organisation. Some of them are at what I would call a site level. So they are specific to a site within an organisation. And we go through this configuration, but the thing to understand is organisation level objects are accessed via the organisation menu. So these are all the things we can configure at an organisation level. They apply globally to my entire organisation. Notice site configuration is under organisation. A site is an organisation object, but then within a site, I can create site level objects. There's no site menu option. So where do I configure sites? Well, I configure site stuff under network. Don't ask me why, I didn't write DUI, but it's called network, not site. But when you think site level objects, think network. And when we look at that actually in the Mist UI, let me just quickly go to that. So, in fact, if I go over here and we go to, let's go to wireless lens at a network level. Anything I go to at a site level, notice at the top I can pick the site. So I can there's different sites I can pick and then see the objects, the site level objects. Whereas when we're at the organisation level, everything's applied globally. So that's a concept that I think is good to get to grips with. So a lot of what we cover on day two is architecture, how we configure Mist, how we get it set up. We talk about claiming APs, which is really cool, and we showed a Mist AI app. I'm not going to have time to show all of that today. But moving on to day three, we talk about configuring wireless lens. Now, everyone's configured wireless lens, so I wasn't necessarily going to show wireless lens today. I want to show you something that maybe you've not seen before. So I thought let's talk about something called WXLAN policies. Before we talk about policies, I'll quickly show you this slide. One of the objects that we can configure inside Mist is something called labels. And here's labels. We get organisation level labels and site level labels. What is a label? Well, a label can refer to things within the Mist organisation. It can refer to users, access points, wireless LANs. But where do we use labels? Well, the main place we use labels is in policies. And organisation level labels are used in organisation policies. And site level labels are used in site level policies. And these are all the things we can create labels on. So with understanding that, let me jump forward in the slides. And let's talk about policies. Because policies are a way of a sort of doing user-centric access control. That is, devices connecting to my wireless network. How do I control what they can and can't do? Okay, and it's quite a simple concept. All rules within a access control policy, what we call the WXLAN policies, follow this format. It is a user or group of users are either allowed or denied access to a network resource. Quite simple. Every rule follows that same pattern. The way we refer to our users or groups of users is by using a label. And the way we refer to network resources is with labels. So this is where labels are used. So I can refer to a group of users or a user by using a label. Now there's a default all users label, and just like there's a default all resources label, or there's our customized ones we can use. So a Wi-Fi client is basically the MAC address of a user, or I could have a list of MAC addresses and refer to multiple devices that a user may use. If I use a wireless LAN label, which points to a wireless LAN, I'm saying all users connected to that wireless LAN. So all users connected to, my guest wireless LAN. Or if I use an access point, it's all users on that access point. So they're just ways of referring to a list of users. I can use AAA attributes as well. So if I'm doing 802.1x and my radiate server is returning an AD group, salespeople or accountants or technical, I could use that group to apply policies to all users that have been returned, that group attribute. And then I'm going to allow or deny them to some sort of resource. So the first thing we're going to do is create labels. So let's have a look at some labels and how we do that. We won't use slides, we'll go straight into here. I'm going to pull up my wireless network in my house to show you this. Here it is. Let's look at some of the labels I've got. So there's quite a few labels I've already got configured. Some of them are a bit more obvious than others, but let's have a look at some ones I've got. I've got this label here. It's a wireless LAN label and it's called Banana Guest. And it is my guest SSID, which is called Banana Guest. I kind of like bananas. So you'll find a lot of things labeled banana inside my house. But that's okay, that's what my network's called. But Banana Guest is my home guest wireless network. You all have guest Wi-Fi networks at home, don't you? Some people looking at me going, you're just strange. Yes, I know I'm strange, but okay. So that's my guest wireless network. And we'll see how I use that a little bit later on. So I've got that. What else have I got? I've got a label called LAN, and it's just my local subnet in my house. As well, I've got my NAS, my printer, all my network devices connected to my switch. So that's my local subnet, and I've called it LAN. What else do I have that's interesting here? Notice these three labels, Luke, Anna, Joshua. They're the names of my children. And if we were to look at Luke, he's my eldest son, you can see there's a number of MAC addresses. They are all my son's devices. His Nintendo Switch, his phone, his Echo Dot that in his bedroom. They're all my son's devices that he owns. And I've got them all under a wireless client label called Luke. So these are some of the labels we can create. Let's look at the policy next. So here are my local policies. What sort of things do I have enabled? You might like, here's one here. Banana Guest and don't forget this is users. So all users who connect to Banana Guest, and I've got not LAN, so LAN in red. They're allowed access to everything but the LAN. They're basically allowed out to the internet, but nothing else. That's what that first policy does. So the way I'm controlling my GETS network is purely with a policy that says if you connect on the GETS wireless LAN, you're allowed to everything but my local LAN. You can't get to my NAS, you can't get to my printer, you can't get to my networking devices, you can only get out on the internet. That's my policy there. And then I've got some interesting policies up here. You can see at the moment that Luke isn't allowed access to TikTok, which is interesting as well, but he was spending way too long on TikTok, so I decided to give him a little bit of time off it. So I can do that. But now I've got these other policies. Now these are greyed out. Anna is not allowed access to anything or resources. Joshua, nothing. Luke, nothing. Why would I do that? Am I a real cruel dad? Now they're all greyed out, they're all turned off, so I'm not being too cruel at the moment. But I don't know if you've got teenagers, or you've ever had teenagers. So Luke, my oldest son, he is 14. And, dinner's ready. And what do? You call upstairs, he's in his pit off a bedroom, and you call up, you go, dinner's ready. Nothing. Luke, do you want to come down for tea? Nothing. Doesn't work. You can call upstairs as much as you like. If you go upstairs, you might go, yeah, I'm coming in a minute. If you're lucky. Can I tell you what? If you disable his Wi-Fi, he's downstairs in a second. It's amazing. Of all his devices, it's the best way to get your children to do things like that. Now, you might go, okay, that's good, but you've got to log on, I've got to click here, I've got to come up here, enable the rule, and that's going to do it for me. But and click save, and that's going to be, that's okay, I can do that, but it's a little bit convoluted. So what about it? Get my phone out, and I say, hey Siri, disable Luke's internet. My phone just said done. If I refresh this page, that rule is now enabled. And now all my son's devices are not connecting to the internet. I'm not going to be very popular if he's at home at what time is it? Yeah. So luckily he's still at school at the moment, so he's hopefully not going to be getting too cross with me at the moment. But now all of his things are disabled, isn't that great? And then if I want to enable them again, hey Siri, enable Luke's internet. Done. That was easy, wasn't it? Let's refresh that screen. And it's disabled the rule. How did I do that? Cool? Well, this is why I said earlier, one of the cool things about Mist is it's API driven. It's easy to do that. Honestly, really, really easy. Let me, now you might go, okay, but I'm not very good at programming, I don't know APIs. You may have seen that in Mist, under, I'm just going to close this, there's a little question mark, and you can do API documentation, but I don't really understand it, and I wouldn't even know where to begin to look in here to find out how to do that. For some people this is scary. Well, let me show you a really quick and easy way of finding the right API call for doing something like that. If you're using Chrome, and other browsers have similar tools, but if I click on the little dots up at the top here, there's, under More Tools, there's something called Developer Tools. Okay? So, little dots, Developer Tools. And inside my Developer Tools, I've put a little filter called API.mist. So it's just going to look at calls to the Mist API. And it's going to tell me all the calls made. So if I click around here, you're going to see calls pop up here. Okay? So if I go back to policy, now the call I want is what happens when I enable this rule. So I click in here, I'm going to enable it, I'm going to stop and clear all my results, and then I'm just going to click save. Because this is what I want to this is what's going to execute that command. So I click save. Oh, I left it stopped. I didn't start it again, that's my fault. But we'll do the opposite. We'll do what happens when you disable it. And there is my request. So it's a put method, which just means you're pushing some data to the Mist cloud. And here, in its request URL, there's the API call. And down here, I can see what it's actually... So if I look at payload, I can also see what it's pushing. And actually, the thing I need was this enable equals false. Because when it's disabling the rule, if I enable it, that'll go to true. So I can do both and just see which element. So I literally just need to copy that and put it into my phone in a shortcut under Siri. It is that simple. So if I just quickly, let me share my phone screen with you. Now, built into iPhone is something called shortcuts. And in shortcuts, you can create different shortcuts. You can see I've got one called Enable Luke's Internet and Disable Luke's Internet. If we take a look at these commands, you will see that link there, that is the link I just copied. So that's all I need to do. I've copied it from my browser and I've put it in here. It's a put, and again, we saw the put in the browser. I've had to put in my unique token, which you can get from your Mist account. That's like your security credentials, just so you guys can't copy this and start disabling my son's internet because you don't have the right token. And you have to say the application is JSON, and then I've got down here, the enabled equals true. That's actually the bit of data I'm writing. And that's it. That is that entire command. If we went to the other one, it looks exactly the same, but I'm now writing false, not true. And now if I can enable and disable that rule as and when I please. It is that simple to get something like this working. So APIs, I think some people think are a bit scary. I would say have a play about with them because you can do some quite cool stuff with APIs. So I wanted to show you that. Let's go through some more of these slides. I'm going to show you something else, which I think we've got time for. And I want to talk about LLM. Sloan's already briefly mentioned the LLM process inside Mist. This is automatically deciding the channel and the power for your Mist APs. Now actually Mist does LLM at two different levels. There's two processes, what we would class as global optimization, sort of global level, and there's local or event-driven LLM. Now global optimization happens once a day in the middle of the night. And this is where the Mist cloud is looking at your entire site and data from all your APs and it's looking at long-term trends, and it's deciding what's the best channel and power setting for each AP. But it's not going to change it all the time, which you don't want. APs changing channels is really disruptive to users. So it does it once a day between 2 and 3 a.m. in the morning. And that's like and those changes are made using Mist's AI machine learning algorithms, and it's looking at long-term trends. And it's only making changes it believes is going to improve your SLAs. Okay? And the main one it looks at is the capacity SLA for that. So is it going to get your users more capacity, more performance? That's what we're trying to answer, and a change should do that. Event-driven SLEs are what we call event-driven RMM is what we call local RMM. It's happening on the AP, okay? And each AP is responding to some sort of event, which is good, because think about it. If I turn on a wireless video camera transmitting 100% of the time right by that AP and it's on the same channel the AP's on, do I want it to wait till 3 a.m. in the morning to respond to that? Of course I don't. I want it to deal with it now, because my users are affected. One use of event-driven, which you're going to see a lot of, is something which we call DFS, which we'll get onto. Now, the reinforcement algorithm, which Sleva talked about, so I'm not really going to talk too much about it, is how the sort of global RMM is determined. What I want to talk about is DFS events, which is affected with the local. Now, DFS, dynamic frequency selection, is a regulatory requirement on certain channels across our 5 gigahertz band. Now, which channels depends on which country you're in, okay, because different regulatory authorities have different requirements, but the rules tend to be fairly the same. And let me just quickly go over what they are. If an AP is transmitting on channel 100, which we see here in this slide, and it's transmitting data, and it detects radar on 100, so it detects a radar pulse, then it is going to switch to another channel. It has to, that's what the law says. And it has 10 seconds to move channels. It's what we call the channel switch time, or the channel move time. Now, in those 10 seconds, it's allowed to finish transmitting any data that it's currently transmitting, so it could maybe acknowledge this data packet. And then it can also send out something we call a channel switch announcement frame, which is a management frame saying, hey, I'm going to change channel, and I'm moving to this other channel. So it could inform the clients, hey, I'm moving to channel 140. The AP will then move to channel 140. Now, if it's moving to channel 140, another DFS channel, it's then got to do something called a channel availability check. Before it can transmit on that channel, it has to wait and try to detect radar for 60 seconds. In some European countries, on some channels, that's actually 10 minutes, the channel availability check. But the default standard one is 30 seconds. And it can transmit for those 30 seconds. That's a minute of no Wi-Fi transmissions. After that period, it can then start sending beacons and start sending data again. The AP is also not allowed to go back to the channel it was on for at least 30 minutes. It's what we call the non-occupancy period. So they're the rules of DFS. So I thought it'd be good fun to actually see how does Mist perform to radar events and do a bit of a live demo. So we're going to have a look inside the Mist UI, and I've got a little, Tommy very kindly has set me up a little environment and brought an AP along for us to have a look at this today. So this is Peter's test chamber with one access point, which is here. And we're just looking at under network, that's our side settings, we're looking at the radio management tab. And when you go to this tab, you'll see there's both 2.4 and 5 gig settings. Now, I'm only using a 5 gig radio on here, so there's no 2.4, but we can see 5 gigahertz, and we can see some information. Here is my AP33 test, It's connected, it's got 5 gig radio, and it's got channel 100, 20 megahertz channel width. I manually configured it for that, just so we could see what channel it was on. But what we can see here is, a lot of you probably know this, but in each Mist AP there's a third radio, which scans all the channels. So we can see from this AP how it sees all the channels in the 5 gig environment. Now we're lucky because in this environment the channels are quiet, there's not many channels being used. When I normally demo this from my home, there's something on nearly every channel. Neighbouring APs, other Mist access points, it's quite a busy environment. But just right here, I can see that channel 100 is used. Channel 104 has some stuff on, 108, 112. I can see the channels currently being used. Now I've ordered these channels best to worst. So my AP is on channel 100, but I can see there's other APs. So if a DFS event happens on this AP, what channel is it going to move to? Well, I'd like to think it's going to move to one of these ones with nothing on. I don't really want it to move to one of these really busy channels, do I? So I actually, now I've got a whole host of channels I could choose from here. Normally when I'm showing it in a more busy environment, I'm going like, well, the best channel's probably one of these 4, and we identify which 4, and then we see does the Mist AP respond as we would expect. But here it could go to literally nearly anything. So, but would I want it to go to anything? Because if it goes to a DFS channel, then it's got to wait 60 seconds before it can operate. If it goes to a non-DFS channel, it doesn't. So if I've got non-DFS channels in my channels that are available, maybe I want it to go to one of those. But let's have a look at what we can see. Further down here, you'll see we can see some events, and these aren't any events at the moment. Now what I've got here is I've got a little device. It's called a Wi-Fi metrics, but it is just a little RF testing tool, if you want to call it that. And one thing I can do on here is generate a radar pulse. So that's what I'm going to do. I'm going to generate a radar pulse on channel 100, and we'll see what happens to our AP. So have to bear with me for a second. And I'm going to generate a pulse on channel 100. Now, while I'm doing this, I can actually, on this machine, I can generate different types of radar pulses as well. In here. But what will happen is, this is going to be picked up by the Mist AP, and it will cause it to move to another channel. Let me just, 1 second. Brilliant. So now I need to, if we're looking under access points, and we look at this access point now, notice it's a channel. It says my access point's on 157. It was on 100 a few minutes ago. Let's go back to our radio management, back to 5 gigahertz. We can see it's now moved to 157. It's on 157. It's way from all these other APs that we can see, which I guess is an 80 meg channel off an AP here. And it's now moved to 157. And 157 is a non-DFS channel. So it's picked one up in the higher 5 gig band that's non-DFS, so it could operate straight away. It's picked a nice clean channel away from all the interference. I would say it's done a pretty good job of doing DFS. You'll also notice that down here we now have an event. Oh, I clicked on it, which I didn't mean to do. Give me 1 second. I need to select 5 gig. We now have an event, and if we look at this event, we will see it's tells me which AP. It's moved from channel 100 to 165, and the reason is that radar was detected. So it's logged it all, it tells me what it's done. We can see that Mist has made a good choice, and we can see that its DFS is working as it should be. So that's just a really quick way of looking at sort of the capabilities of Mist.
I just say 157 on the above channel, and there's 165.
Oh yeah, you're right. It's very good. Maybe it changed channels twice.
Just refresh.
But I'm not sure. Let me refresh. That's what I'm being suggested to do. No? I don't know. That's maybe one for tech support.
Yeah, that could be AP reporting.
Yeah, that might be an AP reporting bug. Good spot. I've not noticed that before. I'm pretty sure it's on channel 157, so it might just be that this has reported it slightly wrong for some reason. But it's still nice that it's moved channel quickly. I've played with radar detection and some other vendor APs, and it's amazing how some of them behave. Some of them don't change channel at all when they're meant to. I'm not going to tell you which vendors and which APs they are. Some of them always move to another DFS channel, so you get disruption on the network because of it. But I really like the fact that in Mist APs not only move quite quickly, they also tend to pick a really sensible channel, and they try to go to non-DFS if they can do. So that's quite a nice thing to see. They were the some of the things I wanted to show you. They're just little glimpses of some of the stuff we look at and we cover on this 4-day Mist class. Great. Well, I will hand back over to whoever I'm handing back over to close down the day. But it's been great coming and speaking with you. So thank you for having me.